It's August 2016, and this is episode 56 of the Unseen Podcast. I'm your host, Paul Carr, and this is, we've been off the air for a little while, trying to get everything together, but tonight we have a special guest, so we moved the time around to accommodate his schedule, and we are very happy to have a nice full panel tonight, and actually a majority international panel that I will introduce in a moment. Just a couple of things. If you have any questions or are all interested in anything else about this podcast, please go to unseenpodcast.com. Our email address is unseenpodcast@gmail.com. You can also comment on the episode at that blog, or you can go to our Unseen Listeners subreddit or to our listeners group at Google+. Now, I would just like to mention that this week has been a big week for our parent podcast, The Wow Signal. We interviewed a young astronomer, just got a freshly minted PhD, Ben Montet, about his research on Tabby Star. If you're all interested in that, and lots of people seem to be, go to wowsignalpodcast.com to learn more. Okay, our special guest tonight is Morgan Rehnberg. Morgan Rehnberg, who is Morgan Rehnberg?
Well, hey guys, thanks for having me. I'm a fifth-year graduate student working at the Laboratory for Atmospheric and Space Physics at the University of Colorado here in beautiful Boulder, Colorado. And I work on the rings of Saturn as part of NASA's Cassini mission. And I also focus a lot of my time on science communication and public outreach. I work with the nationally recognized Fisk Planetarium, and out here on the internet, I am also a regular contributor to Universe Today's weekly space hangout.
Oh, okay. That's pretty popular in our circles. Okay. Also tonight we have Adam Synergy Smith.
Hey, Paul. Great to be here again.
And Chris Prophet.
Hi. Always a joy.
This is, I believe, Chris's second appearance on the podcast. Marsha Barnhart.
Hello, everybody from beautiful Cadillac, Northern Michigan.
Who I should say needs no introduction. And Mateusz Macias.
Hello, guys. Hello, Paul. Hello, Morgan.
Yeah, Mateusz, it's been a while since you've been on, but glad to see you back.
Yeah, thanks. I'm glad as well.
Okay, well, let's get started. Who wants to go first? Anybody?
I'll go first if you like.
Sure.
I'd like to ask Morgan a bit more about his research, what he does studying Saturn's moons and rings, how he does it, and why he does it.
Oh, great question. So Saturn is an incredible system within our own solar system. It's probably the most complicated arrangement of objects that we have in the solar system, because you have not only the second largest planet in the solar system, but you have more than 60 moons, some quite large, others quite small, and by far the largest ring system of any of the outer planets. Now, all the outer planets, Jupiter, Saturn, Uranus, and Neptune, all host ring systems of their own, but all of those pale in comparison to the size of Saturn's. And if you're thinking about, well, why should we care about a ring system at all? I invite you to sort of look out into the universe. And if you do that, what you'll notice is the universe is made up of disks. You look out and see galaxies like our own Milky Way. It's a disk. You look and see the arrangement of the planets in our solar system, and it suggests that our solar system probably formed out of a disk. But all those disks, the protoplanetary disks that we observe far away, the galaxies that we observe even farther away, they're places that we can never actually go and visit in our lifetimes or with our current technology. The only place we can go and actually study how a ring or a disk system actually works is the rings of Saturn or another similar planetary ring system. And since we have Cassini, NASA's spacecraft, at Saturn in orbit now for 12 years, we've had a real front row seat at understanding how these disk systems actually work. And what I do is study the rings of Saturn on the smallest scale. So you can imagine looking through your home telescope or going to your local astronomy club, and you would look through and you'd see a beautiful image of Saturn. You'd see the circle of the planet, and you'd see the big rings surrounding it. This is what we call the main rings. And what you'd be looking at is mainly the A ring and the B ring, separated by a space we call the Cassini division. But those are actually only two of a myriad of rings that are visible to us from Cassini. They're just much, much fainter and more difficult to see with a telescope here on Earth. But even with Cassini, if we take a picture of the rings, the best we can do is make out features in the rings that are about 1 kilometer or so in size. So you can imagine taking a picture and being able to resolve, say, a city block, but not any detail inside of that city block. And that's great for understanding the rings on a large scale, because when your system spans tens of thousands of kilometers, you need to be able to get a broad view of what you're looking at. But if we really want to understand the processes that go on to create the rings that we see, we have to look closer at the individual particles that make up the rings. And these particles are actually tiny little bits of ice. But it's so cold out at Saturn that ice is as hard as rock is here on Earth. So to see the rings on this really, really small scale, we don't take pictures. We use a different technique called the stellar occultation. It's actually almost one of the simplest techniques used in astronomy. Basically, Cassini has a light sensor mounted on it, and we use that light sensor to measure the brightness of a star that we see. Then we watch as that star passes behind the rings. And you can imagine that the more material between that star and our light sensor, the dimmer the star is going to look. And so as we make measurements over time of the brightness of that star, we can understand and calculate the amount of material that must be between that star and us. And that's the amount of material in the rings. And then our resolution is basically only constrained by how quickly we can make measurements. And on Cassini, we can make as many as 1,000 measurements a second of that brightness of the star. And this lets us get resolution that can be better than 10 meters rather than an image, which allows you to only see 1 kilometer or so. And so at the 10-meter scale, we're able to see the processes that are going on between sort of the individual particles that make up the rings. And what Cassini's revealed to us is that what we thought of as a very static system over the course of years or decades or millennia turns out to not be static at all. We see waves going through the rings, we see holes forming in the rings, we see clumps of material that come together only to be destroyed by the gravity of Saturn. And this is painting a picture for us that tells us that even in a relatively simple disk system like Saturn's rings, where you don't have any gas and there aren't any powerful magnetic fields, you still have an incredible variety of interactions going on. And so if we expand that, say, to a protoplanetary disk system where we have some of these complicated factors, then you can imagine that all of the pieces needed for something like the formation of planets are probably there to give solar systems like the one we see today.
Now, go. I'm sorry to step on somebody. I just wanted to ask a follow-up to that. When I was a young student, and we first saw the Voyager pictures from the Voyager flyby, there were these weird sort of splashes over the rings, these kind of triangular shapes. I don't know how to describe it exactly.
Yeah, we call them spokes today. They kind of look like the spokes on a bicycle wheel, sort of going outwards from the center.
Do we know what those are?
So we have some ideas about what those are. And one idea that we have is that the very, very top layer of Saturn's rings gets electrically charged. And then that interacts with Saturn's magnetic field. And as Saturn rotates, its magnetic field rotates, and it causes these particles to move in this spoke-like structure. Now, Saturn's magnetic field is relatively weak for a giant planet. It's similar in strength to the Earth in comparison to Jupiter's, which is many, many, many times more powerful. And so thankfully for those of us studying the rings themselves aren't terribly affected by the magnetic field. But that very, very top layer might have this sort of passing interaction at certain times, and that we think can yield the spokes that we see.
Okay. So Mateusz, you have a question?
Yeah, Morgan, from the data we have, do we know how did the rings formed and how far ago? When did they form?
That might be the most important question that we haven't yet answered, but it's one that we're on the way to trying to answer. And so first, let me set up why we're having trouble answering this question. If we look at the rings and we measure the composition of them, we find that they're extremely pure water ice, like 97, 98% pure water ice. And we know from observing other bodies in the solar system that space is actually relatively dirty. And if you've been exposed to space for a long time, then you tend to get pretty dirty on your surface. And so if the rings were billions of years old, we would expect them to be dirtier than 2 or 3% contamination. On the other hand, the only plausible mechanism we have for forming the rings can only take place at the very beginning of the solar system. And so we have this tug of war between the observation, which is telling us the rings must be hundreds of millions of years old, not billions, and the explanation, the theory, which is telling us, well, we couldn't have gotten rings unless they were billions of years old. And one possible reconciliation of these is if the rings are a lot more massive, there's a lot more material in them than we've previously thought. Because you can imagine that if you have lots of material in the rings, then dusting them on the outside with space dirt, and then they kind of recycle that material, mix it in with the rest of the ring, and you could do this for a very long time and still maintain a few percent purity. The problem is we don't know the mass of Saturn's rings to better than like a factor of 10. And that's because although they're the most massive rings in the solar system, they weigh almost nothing in comparison to Saturn itself. And that makes it very difficult to measure them. But at the end of the Cassini mission, what we call the proximal orbits, or the grand finale, Cassini for the first time is actually going to fly between the rings and the planet. And we hope that this will allow us to make the first ever measurement of the mass of the rings. And we'll do that by measuring the speed of the spacecraft and how it changes as it passes the rings. You can imagine the heavier the rings are, the more they'll deflect the spacecraft as they fly by. And so by making this measurement from Earth, we hope to observe the mass of the rings. And for the first time, that'll help us understand which of these possible theories might be right.
I have a question.
Okay.
The formation of the moons that have been captured by Saturn, how can you tell their age and gauge that with perhaps against the rings? What mechanism do you have to study the relationship there?
So we look at the moons of Saturn and we can kind of group them into 3 categories. The first category has only one member, and that's Titan, Saturn's largest moon, and perhaps the most Earth-like place in the solar system. It's got liquid on its surface, it's got a thick atmosphere, it's got, we just saw this week, perhaps valleys and river channels and things like that flowing over its surface. So this is a moon that had to have formed at the beginning of the solar system. And we think in the past, maybe Saturn had more moons like this, and they were disrupted to form the rings that we see today. The second class of objects that we can break the moons up into are moons that might have formed from the rings themselves. We look at some of the inner moons of Saturn, and we observe that their density is actually lower than the density of ice. And this tells us that since the rings are made nearly 100% of ice, that probably these moons formed from the rings, very similarly to how planets in our solar system probably formed from the protoplanetary disk billions of years ago. So we have this group of moons that has densities basically the same as the ice cubes in your freezer. And then the third group of moons are what we would call the irregular satellites. And all of the outer planets have these guys, and they tend to orbit on sort of random trajectories with high angles of orbit, very elongated orbits. They sometimes orbit backwards, and they tend to look like asteroids. They're rocks, they're kind of potato-shaped. And we suspect that these objects were probably captured by Saturn either early in the solar system or subsequently. And there's no good way to really tell for any particular object when that might have happened. we can use models of how the solar system might have formed to estimate the number of captured asteroids that a planet like Saturn might have. But that's a very aggregate estimate, not an individual guess for any particular object. Of course, the icy moons couldn't have formed until after the rings had formed. So once we understand when the rings have formed, then we'll be able to put some limits on when we think these icy moons might have formed.
Now you got to tell me about Hyperion. How did it get like that? It looks like a sponge.
Yes, Hyperion is a very strange looking moon. It really does. If you've never seen Hyperion, go look at it. Cassini's taken some gorgeous images of Hyperion. It's very sort of sponge-like is the best way to describe it. And the truth is we don't know how Hyperion formed, but a good hypothesis would be that it formed very slowly and isn't really a solid object. And we actually think this is probably true for many asteroids in the asteroid belt. It might also be true for comets like 67P, Churyumov-Gerasimenko that Rosetta has been observing. And instead of solid objects, we like to think of them as what we call rubble piles. And these are basically sort of semi-connected aggregations of material that are held together sort of gently by their own gravity. But if you were to come and whack them with a giant sledgehammer, they would tend to break apart rather than to ricochet. And so how Hyperion got to look like it did is a mystery, because it looks basically nothing like any object we've ever looked at before. But probably a moon like Hyperion didn't form in the orbit of Saturn.
Okay. So there's more to learn about Hyperion.
Absolutely.
Because we've flown by a few asteroids. We haven't seen anything quite like that.
Nothing remotely like that.
I'd like to just point out for those of you listening live, the Q&A is on. So if you want to ask Morgan a question, shoot it through the Q&A. Okay. Are we done on Saturn, or anybody wants to continue with that?
Yeah, I have one more question. I know Cassini is still up and running, but do we have any plans for any future spacecraft flowing to Saturn?
So there are no plans right now for future spacecraft to go to Saturn. No plans as in we're putting together an actual mission. But every 10 years, the planetary science community gets together in the United States, gets together and publishes what we call the Decadal Survey. And it's basically our roadmap for the next decade of where we want to be focusing our energy as a community. This is important because as a field of study that's funded primarily by the federal government, it helps to have this long vision of where we want to go when we, say, get up in front of Congress. And every Decadal Survey ranks the small, medium, and large missions we'd like to see happen in the next 10 to 15 years. And one of the medium-class missions that has been included by planetary scientists on their wish list of missions is what we call a Saturn Probe. And the idea here is less to study the rings and moons of Saturn and more to study the atmosphere itself by creating a spacecraft that could plunge down into the planet and make measurements of the atmosphere as it went down. Now, probably any mission like that would also have a component that's orbited Saturn and would be able to take further measurements. But nothing on the scale of Cassini is planned for Saturn in the future. Right now, we're starting to think about, of course, Europa. That'll be our next large mission to the outer solar system. And then in the early stages of planning, there's a mission to Uranus. And now that we've studied Jupiter, we've studied Saturn, we're ready to go out to Uranus, which is twice as far away from the sun as Saturn is, and apply the same sort of bring everything in the kitchen sink idea that we did with Cassini that's worked out so well for us in the last 12 years.
Right. Now, we should point out for folks that may not be quite up to speed on this, that Europa is a satellite of Jupiter, not Saturn. Jupiter has been studied, it has had two orbiters, and is about to get a third. No, it has a third now, actually. Has this third orbiter. Juno, yeah. So Jupiter gets a lot of attention because it's close.
Yeah, it's much easier. It's 4 times faster to get to Jupiter than Uranus, so you have to make a pretty compelling case for why you want to go to Uranus when there's so much we still don't understand about Jupiter and Saturn.
I remember many years ago, Alan Stern proposed a Uranus flyby using the same spacecraft, essentially. Of course, it'd never be the same, but that flew by Pluto, the New Horizons mission.
I was talking to Alan maybe last year, and of course, Alan Stern is the principal investigator of New Horizons. And when you put a mission together like that, you have to cover all your bases. And one of the bases that they had to worry about is what if the mission gets delayed and we can't go to Pluto? Because they had a very narrow window for going to Pluto. And so they had put together an entire mission plan for New Horizons to become a Uranus mission if their window to Pluto closed. And so that thinking will help us lead into a future Uranus mission that'll be an orbiter much like Cassini at Saturn or Galileo at Jupiter.
Yeah. Well, didn't the Voyager missions show anything in that arena, or they just were incapable of gathering data? I mean, we
absolutely saw Uranus with Voyager 2. So Voyager 1 left the solar system after Saturn. It never flew by Uranus and Neptune. But almost everything we know about Uranus today and Neptune today comes to us from Voyager 2. And it showed us this very smooth, featureless surface, the fact that Uranus is tipped on its side so that its rotational pole points towards the sun instead of sort of perpendicular to the sun, that it has a ring system. And we've been able to study that ring system with the Hubble Space Telescope in the last couple of decades. And also that it also has a collection of moons around it. We don't know of as many as Jupiter or Saturn, but that's mostly because we haven't been there for years looking for moons.
Mm-hmm. How about you, Chris?
Well, I've heard today that they discovered the spot, the big red spot on Jupiter. The temperatures above it is quite Earth-like, but just in that area, right? I just wondered if you'd heard anything about that, or what could possibly cause it, because they were saying there might be some interaction between gravity waves and sound waves, which are causing this high temperature sort of blip. But any ideas?
So atmospheres are incredibly complicated things. Even here on the Earth, we don't really fully understand how our own atmosphere works, and that's one of the major impediments to predicting the weather 2 weeks from now. And the interaction, the movement of the air and an atmosphere, as well as the composition of that atmosphere, which can change the higher up you go, can create these weird pockets of temperature. So, for example, in our own atmosphere, as you go up in the atmosphere, it gets cooler. We've probably all flown in an airplane and put your hand against the window and you feel it's colder than it was wherever you took off. But if you go high enough up in the atmosphere, it actually starts to get warmer again. Then it gets colder again. Then it gets warmer again. And so the atmosphere can actually trap in heat with certain, depending on the combination of the density of the atmosphere, the composition of the atmosphere, the movement of the atmosphere. And there are places high in the Earth's atmosphere that are like 1,000 degrees in temperature. Now, there's not a lot of atmosphere there, so it's not like you could stick a pot of water out the window and boil it. But there are areas that could be very hot on in any atmosphere, and that would extend to an atmosphere like Jupiter's.
One other thing for me on Saturn is Iapetus. I mean, how did it get that spare tire?
Yeah, so if you've never seen a picture of Iapetus, it has this kind of weird ring, like ridge around its surface, and it's difficult to explain. This ridge is way, way larger than it should be for the size of the object, and it's somewhat difficult to explain how that ridge might have come along. One idea would be that there was some sort of large impact. Another idea could be that at some point the moon was spinning, like during formation, the moon was spinning very quickly, and things at the equator tend to bulge out of a spinning object. But there's really no compelling evidence one way or the other for Iapetus. Another confusing thing about Iapetus is has the highest contrast ratio of any object in the solar system. And what I mean by that is one side of Iapetus is extremely dark, and the other side of Iapetus is extremely bright. And this is something that was first observed in detail by Cassini. And this tells us that there must be different material on the surface of these two sides. And what we think probably happened was that at some point there was like an icy type material on one side of Iapetus, and eventually that ice evaporated away, sublimated, and left behind the dirt. It's kind of like during the winter, you get that snow from the snowplows, it's all mixed in with dirt. Eventually that snow melts and you're left behind with all those piles of dirt. And if that happened at Iapetus, it would leave that area much darker than the other side of the moon.
But why would one side melt and not the other?
So, well, it's possible that there was extra ice on one side than on the other. Perhaps at one point, Iapetus had ice come out from underneath the surface for some reason on one side, early in its formation, for example. It's also possible that ice volcanoes, like what we see on Enceladus, happened somewhere in the Saturn system that was able to coat one side or more of Iapetus with this material. If all this sounds somewhat implausible, it's because we don't really have a really good idea of what's going on at Iapetus.
Morgan, could that ridge be possible because of some active geology history before? Because, we flew to Pluto and we found that it has mountains. It used to have active geology in the past. And for the object so far from the sun and from any bigger object like Jupiter or Saturn, we never thought that it might be possible.
It's absolutely possible because there's no real evidence that this ridge is particularly young. And so many objects in the solar system might have been geologically active early on in their history. In order to be geologically active, what you principally need is a source of heat. And all objects are warmer earlier in their life and cooler later on. It's just the big objects have enough internal heat to stay warm for a long time. So Iapetus could well have had some sort of active geologic process happening early on in its history that perhaps forced ice up through the surface to form this ridge, and then that ice solidified in that ridge-like shape as the heat began to dissipate. And then for millions or billions of years, Iapetus has basically kept that solid shape. We see so much variation in just the Saturn system alone, not to include Jupiter or Pluto or any of these other places, that it certainly seems like a whole range of geologic activity must have been happening to these objects around or over the course of the history of the solar system.
Hi, Morgan. Just following on from that, it's actually been discovered there's still geologic activity on a lot of these worlds, like I think we said Pluto, there's cryovolcanoes. Enceladus, there seems to be plumes there, which seem to be driven by underground heat. So how is the standing on that? How do they explain this internal heat being generated? Because before they said, it's leftover heat from the formation of the solar system, but that doesn't seem to be the case anymore. What's the thinking on that now?
So there's basically three sources of heat that you can get in the outer solar system. The first kind of heat is impact heat. This happens when you're forming, you have all the pieces of yourself smashing together, you're turning that velocity, that kinetic energy, into heat energy. That can also happen later on if you get hit by a big rock, like what happened, for example, with the Earth during the formation of the moon. That heat tends to be one big jolt and then kind of fleeting. And so we generally don't favor that as an explanation for a lot of phenomena. A second form of heat comes from the decay of radioactive isotopes, or things like uranium that was spread throughout the protoplanetary disk billions of years ago when our solar system was forming. Every object got some of that. And as that radioactive material decays, it releases heat. It releases more heat early in the history of the solar system and less heat overall. The third source of heat, and the only one that's replenishing, is tidal heat. And tidal heat works in basically the same way that our tides work here on Earth. It's where it gets its name from. You can imagine that as the Earth rotates, the oceans pass under the moon. The moon's gravity kind of lifts that water up, and then as we rotate the Earth some more, that water falls back down. We get high tide, we get low tide. But the moon's relatively small and relatively far away. If you go to one of these outer giant planets that are, hundreds of times larger than the Earth, much less the moon, you can lift up the whole surface and sort of squish and stretch the whole moon itself. And we see this most dramatically at the Jupiter system with the moon Io. And Io is the most volcanically active place in the solar system because Jupiter is stretching it and squeezing it and stretching it and squeezing it. And at any given time, we can observe multiple volcanoes shooting material off of the surface of Io that covers the entirety of the Jupiter system. This is the source of heat that we think makes the liquid water ocean under the surface of Europa at Jupiter. That's why we're sending a mission to check that out in the early 2020s. And this is also the form of heat that we think is powering the ocean and the geysers on Enceladus. But there's a bit of a puzzle at Enceladus because Cassini carries basically a thermal camera on it that's capable of measuring the heat of different objects. And when it measures the heat coming out of Enceladus, we find that there's more heat coming out than we can explain based on the tidal heating that we expect to see. And even if you throw in the radioactive heating that an object the size of Enceladus should have, put those things together and we're still missing heat from somewhere in the solar system. And so we think that there's more going on than we understand. And this has really been compounded by our observations of Pluto. I think everyone from the leader of New Horizons, the mission that went to Pluto on down, would have told you that the best bet at Pluto was to find kind of a dead icy world. And it could have been a remarkable dead icy world, but it was going to be a dead icy world. Instead, we see this big heart-shaped feature on the surface with no craters on it, telling us that it must just be a few million years old. And a few million years, that's a long time, but it's a short time in the geologic sense. And something that's been changing in the last few million years, that's not an icy dead world. And yet there's no way for Pluto to get this tidal heating because there's no giant planet out there to provide it. And so we're really having to sort of sit and reevaluate how we understand heat in the solar system. Because clearly we're not understanding the whole picture of Pluto. We're not understanding the whole picture at Europa or at Enceladus. And it's possible we're not understanding the whole picture elsewhere in the solar system as well.
Okay, so you're moving slightly towards Marvin Herndon's idea, whereby there might be like a georeactor, some sort of active nuclear heating inside these bodies, perhaps, because that would explain how there's heat on Enceladus and Pluto and even Earth. I don't know. He's a little bit out there, but he seems to be coming more closer into orbit now.
Yeah, well, I should be clear that this is not my area of study, and so I'm probably not well placed to evaluate alternative ideas about the source. I just know that so far we haven't accepted any hypothesis that sort of fully explains all the observations that we're making in the solar system.
Okay, thanks.
Yeah, okay. Well, now, you mentioned Enceladus a few times already. That's a good segue into sort of our next topic, which is search for life in the universe. I know Enceladus is I know Carolyn Porco has been pushing that as an astrobiology target. Can you maybe give us in terms of the most hopeful approaches for finding life in the universe, give us like the top 5 or so.
Absolutely. So there's sort of two paths here. There's, are we looking for evidence of life whenever it might have occurred? Or are we looking for evidence of life that's actually alive today? And if we're looking for evidence of life today, we need to go somewhere that meets the needs of life here on Earth, because that's all we can understand. That might not be the only kind of life out there in the universe, but every bit of life we see on Earth needs a source of energy, needs a source of liquid water, and it needs a source of organic material, of carbon, for reproduction and to incorporate into its own structure. And every bit of life on Earth, no matter how strange and unusual, requires those three things. And so we can start evaluating places in the solar system based on whether they have those three things today, or whether they might have had those three things earlier on in time. And so if we move outwards from Earth, the first place that we would come to is Mars. And this is the place we've studied the most for evidence of life so far. And that's mainly because it's the closest and most easy for us to reach. And today, the evidence suggests that the conditions on Mars aren't great for sustaining life as we understand it on Earth today. But in the past, we think that Mars probably resembled a lot more like Earth than it does today. It could have had liquid water on its surface, could have had a thicker atmosphere. There's lots of carbon dioxide, so that's a source of carbon compounds. Of course, it's still relatively close to the sun, and so you have a source of heat and energy, the same sorts of things that photosynthesizing bacteria use for basic reproduction and energy generation here on Earth. So Mars is probably not a bad idea for a place to look for past life, but not high on my list of places we're likely to find life today. If that was going to be our criterion, then the best places to look would be the places that we think have oceans of liquid water. And the two that we're most certain about are Europa at Jupiter and Enceladus at Saturn. And these have liquid water. They have a source of energy. We just talked about tidal heating. That injects a lot of energy in the form of heat. And there's life forms here on Earth that can basically take heat and convert that into the energy of life. So that leaves us with the question about what about carbon? And this is where Europa might be a better candidate than Enceladus. Because I mentioned earlier this moon, Io. And Io is shooting volcanoes out into space, covering all the other objects in the Jupiter system. And what is volcanic ash? Well, it's mostly carbon-based compounds. And so we see these large cracks and stripes on the surface of Europa. And we think these stripes might be patches of organic material on the surface of Europa. And we think these cracks might lead down to the ocean underneath the surface. And over time, as geologic processes sort of turn over the crust of Europa, you can imagine some of that carbon being sort of pulled down under the surface and eventually filtering its way down to the ocean. And then you have liquid water, you have a source of heat, you have a source of carbon. Those are the three things we think that life needs to survive if it's going to look like life here on Earth. One other place that I think doesn't meet necessarily those three requirements, but is a really tantalizing place to look, is Titan. Because as I mentioned before, Titan is the place in the solar system that most resembles planet Earth today. It has an atmosphere that's about 1.5 times as thick as the Earth, so you could actually walk around on the surface without a pressure suit, and you'd be just fine. It has liquid flowing on its surface, and it has a very active liquid cycle. Now, I'm being careful to say liquid cycle because it's not water. Water is so cold out here that it's going to be as hard as rocks in the form of ice. The liquid on Titan is methane. Its atmosphere has methane in it. Its surface has lakes of methane, rivers of methane. We think methane rains down onto the surface. Of course, methane itself is an organic compound, so we have plenty of organics on Titan. We even think there might be lightning on the surface of Titan, and some have suggested that lightning was a key catalyst to sort of get that chemistry of life started here on Earth. And so although it doesn't have liquid water, if we were looking for a place in our solar system that would form life that's very different than Earth life, but still sort of a plausible home for life, I think Titan's the place to look.
Does Titan have an internal heat source like Enceladus?
So Titan, as one of the largest moons in the solar system, has a lot of radioactive elements within it. And so it has radioactive heating that's been able to sort of maintain its heat throughout sort of the history of the solar system. And we even have evidence from Cassini that there might be volcanism happening on the surface. Now, the working liquid, the lava in this volcanism, is actually liquid water. instead of liquid rock, which is like what volcanoes are here on Earth. And that gives us some evidence that if you do see volcanic activity, there must be internal heat still within Titan.
Do they have deep ocean vents underneath all those methane lakes?
So we don't know because it's hard to see down. We think the oceans aren't terribly deep, at least the ones we've been able to study, and that's only sort of in the most passing of detail. We think they might be something like 20 meters deep. So we're not talking about deep oceans like what you would see on planet Earth, or deep oceans like what you would see on Enceladus or Europa. Europa, for example, has oceans that we think might be 100 kilometers deep and contain more water than all the oceans and lakes and rivers on Earth combined. That's a really promising place to look for life. The last thing I think that I'd say about the search for life in the solar system is that it's important to draw a distinction between where life could survive and where it could arise. Because we've seen all sorts of amazing adaptations here on Earth for places that life lives today. But we don't think that almost any of those places were places where life originally formed. And if life is as sort of difficult to get off the ground as it certainly seems to be, then you can imagine that we need the absolute most ideal conditions to give ourselves the best chance to get that basic chemistry of life going. And so even if we have a sort of quote unquote habitable place elsewhere in the solar system, be it Enceladus or Europa or Titan or even Mars, and we could maybe transplant Earth life to any of those, it's not clear that the conditions there are such to really make it favorable for life to actually arise on one of these other worlds. And that's one of the big questions we have to kind of try to answer.
Okay.
Now, don't you kind of think, I'm a big panspermia advocate, so isn't it most probable that there are all types of bodies that are transiting out there that impact and carry with it and give birth to conditions or bringing types of life that had not existed before but are now delivered to a system from another object? How much does that factor into this search for life, this panspermia aspect?
Absolutely. We observe material exchange between especially the inner planets all the time. You know, we have lots of Martian meteorites here on Earth. Those are bits of the Martian surface that were blasted off and eventually fell back down to the surface of the Earth. We're pretty sure that the moon is host to all sorts of Earth meteorites, bits of rock that asteroids have blasted off the Earth, for example, the asteroid that killed the dinosaurs, and that material then falls onto the moon. And so it's not difficult to imagine that if you blast a piece of the Earth off and it lands on another world, that bit of Earth might carry all those Earth bugs inside of it that we know live in basically every cubic centimeter of the Earth's crust. The question becomes whether that life can survive the journey between locations, because it probably takes at least tens of thousands of years, and maybe as many as millions of years, for these objects to leave one world and come in contact with another. And over that period of time, you're going to be subjected to intense radiation, intense cold. That's after the intense heat of this explosion that blasted you off the surface. You're going to have no pressure. That's very tough for bodies to survive. You're going to have no liquid water because that will have boiled away in this no pressure environment. And then ultimately, you're going to smash back down and form a crater on another world. And so certainly the odds are stacked against you if you're an organism trying to ride a space rock from one planet to the other. But it's not impossible. And we can't rule out panspermia. And this brings us to sort of the deeper philosophical question of the search for life, which is how will we know when we found it? Because if we find life, say, on Europa, and it looks anything like life that we have here on Earth, how will we be able to answer whether this was contaminated presence on the Europa exploring spacecraft, or panspermia traveling from the Earth to another world, or the fact that we happened Earth life happened to develop in the most efficient way possible, and therefore we would expect that other life that arose independently elsewhere in the universe would also develop along those same lines, because that's just the simplest, easiest path to take. We might find examples of life all over the place, but we might never know for sure unless we find something that looks so completely unlike anything seen on Earth that we've actually found life. And how do we look for something that looks so completely unlike anything we've seen on Earth? That's a really tough challenge to undertake, especially since we're still sort of trying to nail down what it means to be alive here on Earth. Are viruses alive? Are donkeys alive? These are, questions that don't fit our basic definition of what it means to be alive. And if we can't nail down definitively what it means to be alive here on planet Earth, how are we ever going to be able to figure out what it means to be alive if you're a totally alien creature on another world in the galaxy?
Well, isn't that one of the big hopes for that Titan would, if there is life on Titan, it would have radically different chemistry.
But how do we find it? Absolutely. That Titan might have much different chemistry because of the lack of water. But how do we, design an experiment to recognize that life? If it does do chemistry completely different than us, then any chemistry we might try to do to analyze that life could end up just destroying it. Or it could just be totally unresponsive to that life. If you take Earth life and you put it in presence of some argon atoms, nothing happens because argon is inert and doesn't interact with living things here on Earth. So if you're an alien trying to test for life by putting it in contact with argon, because that's what worked on your world, that might return a negative signature here on Earth, even though we know the Earth teems with what we would consider life.
Okay, well, that leads me to something that's always fascinated me, which is there's been at least one positive signature. I don't know if how well versed you are on this, but Gilbert Levin's labeled release experiment.
Yes, absolutely. So this was an experiment on one of the Viking landers, which landed in the mid-1970s on the surface of Mars. And they were thinking about these very questions. How do you discover life on another world that might look very different than life on Earth? And one thing that they hit on was likely all forms of life require energy. And this, to have life sustaining, you basically have to bring chemicals into your living thing and eject chemicals out of your living thing. And so what they did was they took little drops of liquid that basically was the kind of stuff that we grow bacteria in the lab here on Earth. And they tagged it with radioactive elements, things that didn't occur naturally on Mars. And they basically took a sample of the soil and they mixed it in with this liquid. And their guess was that if there were living things in this sample, it would pull in that liquid to try to gain energy from it. And then it would release as a gas the waste products. And these waste products would include this radioactive element because life doesn't have a need for that radioactive element since it doesn't occur naturally on Mars. And then they could test the air above this sample for this radioactive element, and that would tell them that life had been found. And they ran this experiment on both Mars Viking landers, and one of them came up positive, saying, yes, we see gaseous form of this radioactive element. But then they ran it again on that same spacecraft once more, and they found no evidence of that radioactive element the second time. So they did it 3 times in total. One of them came up positive. They also had other experiments on Viking capable of detecting life. One of them was just trying to detect the amount of organic material, assuming that any life on Mars probably has some sort of organic foundation. And in none of those experiments was any organic material ever discovered. Even in the sample that returned a positive value for this radioactive material, suggesting that life had incorporated it, no organic material was found at that site. And so the overwhelming consensus of scientists today is that some non-biologic process caused this result to turn positive. And this is a real warning sign for us as we try to discover life elsewhere in the solar system and in the galaxy. We might see something that looks like the signature of life on Earth, but there's a plausible way to generate that with a non-living mechanism. And again, that throws some ambiguity into how will we actually know that we found life.
Mhm.
Okay, I got one thing I can add here. I looked at this for my book, and it seems to me that we might send out instruments to detect for life, and you may get positives or negatives or whatever. But the only way you're really going to be sure is if we actually go out there and verify it ourselves, because we're so much more adaptable with what we can do in place. And that's why it's so exciting what's happening with Mars at the moment. It looks like it's getting closer all the time, some sort of Mars mission. And then we can actually, because, I mean, if people on Earth can't agree whether something is right or wrong, you know, and they're standing next to one another, if there's an instrument on Mars and something's going on out there, it's never going to happen. We need to get out there. That's my view anyway.
There's no doubt that a human mission to another world would be incredibly more flexible than any of the robotic explorers we've sent so far, or ones we can even envision sending in the near future. They would be able to rely on human ingenuity, human observation to figure out what's going on and to match patterns that we're not anticipating, and thus we couldn't program our robots to look for. So I think that we could make huge gains in trying to search for life by sending humans out there. But we also have to keep in mind that we bring all our human life with us. You know, we have an incredible number of living things on the surface of our skin, on the inside of our bodies. And when we bring that to another world, we have to be even more careful that we keep that separate from the world we're exploring, or we'll introduce this ambiguity once again.
Our dirty meatbag bodies, as
That's
it's
right.
described. Okay. I wouldn't give up hope on Mars, though, for life, because I read a study that the core's still fluid. So that means there's some sort of internal heat. So water could be down there. There's heat, you know. If life
it's possible.
surface,
Absolutely.
it's possible, yeah. But it's a deep search, that one.
Yes.
Okay.
So, following on from that, when are we going to see a manned mission to Mars? And who is going to get there first?
Well, I can have a go at that one. This is my specific area. I don't know if that's okay, Morgan. Right. Well, at the moment, NASA is sort of saying, you know, 2030s. It's looking mid-2030s. Maybe it's going to work out a little bit later than that. Whereas other people with more aggressive schedules, like Elon Musk, are saying 2025. But quite often he's very ambitious, shall we say, in setting these schedules. And it's very interesting because in the past we have the only analogy we have is that Apollo worked because and it worked because it was backed by a big government. And so most people believe that it can only be done, these sort of big projects can only be done by big government. But Elon he has his ways, and there's something to be said for having just one company focusing on it. Because if you have NASA, then you also have Roscosmos and you have ESA, and they get together and they have a big meeting, and it might take 5 or 6 years to work out what they're going to do. It's sort of a NASA guy went down to SpaceX when they were developing the Pico X, the heat shielding, and there was a small meeting with Elon, and they all described what they should do with this Pico X, and Elon said to the NASA guy, well, you haven't said anything yet. He says, well, I'll just let everybody have his say. It's normal for NASA, you know, protocol. And Elon says, well, tell me what it is you think. And he says, well, this is the best idea I can come up with. And Elon leaned back in his chair and he says, right, we'll do it. And then the meeting ended. Everybody knew what they were going to do. They went away. There was and it was like a half-hour meeting. And the new SpaceX heat shield is like 2 or 3 times better than the original one. So there is something to be said for individuals, but there's also something to be said for NASA. So I don't know, maybe there's going to be like a synergy of the two. You know, there's something NASA can bring to it and something that SpaceX can bring to it. So, but I don't know, 2030 maybe? 2030 seems reasonable. That's what it seems at the moment.
What's the planetary protection officer at NASA going to say?
They're going to be doing backflips like Scotty dogs, I think, really, when the SpaceX come up, because they want to go to the areas of special interest where there's water, and of course the Planet Protection do not want them to go to the areas.
Right, those are the areas that are
water.
forbidden for robots to visit. Yeah.
Some of the news that came out just a couple of weeks ago, I think, has put a real damper in my mind on the feasibility of going to Mars relatively quickly. Because there's a study that came out just a couple of weeks ago that said that Apollo astronauts who went to the moon are dying of heart disease at rates like 4 to 5 times higher than other astronauts in the Apollo program who never left to go to the moon. So this is the same well-qualified, healthy population of people.
Yeah, but that's a very small population.
But spending less than a week outside of the confines of the Earth's protective magnetic field clearly did significant damage to their bodies. And if we're going to Mars and back, much less talking about staying on Mars, we're talking about hundreds of days exposed to the Martian or to the sort of planetary radiation field. And this causes a big problem. It's not insurmountable. There are technological ways we could get around this, but you add in this complication and you're slowing down, I think, the rate at which we're going to be able to move towards getting human missions. And NASA's idea of sending humans to orbit Mars and come back to the Earth and do nothing else, that's sort of criminally malpractice in my mind, because you're sending them to do nothing that a robot can't do, to put themselves at extreme danger. And that's not the right way to approach it. If we're going to send humans to another planet, we have to have a mission for them to do that we can't do robotically. And then they have to go and do that because they're going to put themselves at risk, whether it's from radiation or from just bad luck with mechanical problems or launch problems or any number of things. And the only way we can ask astronauts to do that is if they have a meaningful job to do. And simply sitting in a capsule for 500 days, flying to and from Mars, that's not it. And that's not the right way to go.
Yeah. Now I'd like to point out I'm pretty skeptical of that study because it's such a small sample size. And, Buzz Aldrin is 86 and very robust. So
I do have something to throw in there. That it seems I've gone into a bit of a research on this one, that clinicians know that there's a problem with exposing people with radiation. It causes veins to thicken. And that puts extra stress on the heart. And it seems that some of these iron cosmic rays, which are just a nucleus of an iron atom moving at relativistic speeds, they're pretty hard radiation. But of course, every problem, there's a solution. I understand there's NASA's working on nanotubes, boron nanotubes for high radiation resistance, and various other people doing magnetic shields to shield the spacecraft from this high energy radiation. So and there's other
one great idea is to surround the astronauts with the water they need to drink. If you're going for 500 days, you need to take a lot of water with. And if you've ever been to an aquarium and tried to use your cell phone, you realize that water absorbs radiation very effectively. And so if you could somehow build a spacecraft that the lining of the spacecraft is the tank for the water, then you could protect the astronauts and carry the water they need to drink. But that's a big departure from the way we've built spacecraft in the past. And so each one of these sort of engineering hurdles is just going to add some time. And if we're talking about NASA, we're talking about every time we add a year to the project, that's another chance for a new president or a new NASA administrator to change their mind. And just look from President Bush through President Obama, how many times NASA has sort of changed its primary mission. We had Constellation, we're going to the moon, scrap that. Now we have the Space Launch System, and we're going to go collect an asteroid, but I don't think very many people in the scientific community think that project will ever actually happen. We've already started talking about going to Mars, but will a future President Clinton or President Trump decide to divert the human space program back to the moon as a testing ground for going to Mars? And we sort of just go in circles. And every time we add another year to this mission, we add another opportunity to get off track. And I think that's one of the more compelling reasons to think that NASA might not be the first entity to get human beings on the surface of Mars.
Now, Mateusz had something he wanted to add, so go ahead, Mateusz.
Yeah, I wanted to leave Mars for a little bit. I want to go to Europa. Morgan, how do you think it's the best way to actually drill through the ice and go to the ocean? And how complex life can we find there?
So how to get to the ocean underneath is a tough question. And the first step is to understand how deep the ocean is underneath the surface. And this is something we don't understand very well. I think right now a fair estimate would be that it's 10 kilometers plus or minus 5 kilometers under the surface. So that would be anywhere from 5 to 15. It's a good ballpark estimate. But it could be as deep as 100 kilometers under the surface. And so this mission we're sending to Europa in the 2020s has a very important instrument called ice-penetrating radar on it. And this ice-penetrating radar is going to blast the surface of Europa with radar and watch it bounce back. And we know from using radar here on the Earth that when you cross that solid liquid boundary, you reflect radar waves very noticeably. And so we'll be able to tell, hopefully, how deep that ocean is by the 2020s with this Europa mission. And that'll help us understand how challenging it would be to bore through the surface. Now, it's almost certainly many kilometers deep. I don't think there's very many people who think it's less than 5 kilometers beneath the surface. And that's, as deep or deeper than we've drilled here on Earth. And so there's no way you can take a 5-kilometer drill bit with you on a spacecraft that has to weigh a few hundred kilograms. Probably the best idea that I've seen is this idea that we basically put the spacecraft, the probe, into some sort of capsule, and we heat the tip up, and we let it melt through the surface. And over time, it just melts farther down. It sort of trails some sort of radio antenna behind it, and eventually it plops down into the ocean below. This would be an extremely slow process, and it would require a tremendous amount of energy. We'd need some sort of radioactive energy source on board the spacecraft in order to do this. But until we know how deep the ocean is, it's difficult to put estimates on how difficult that would actually be.
Well, now, some of those cracks on Europa, are they a possible entryway?
Maybe. We don't know. If the crack is a kilometer deep and it turns out the ocean is 10 kilometers under the surface, then sure, we've saved ourselves 10%, but 9 kilometers is still farther than we know how to drill through. And so this Europa mission is also going to be mapping the surface at a very high resolution. And it'll help reveal the places where the crust is the thinnest, the ocean might be closest to the surface, and the places where it'd be safest to land a spacecraft. And so you can think of this mission as really laying the groundwork for all future exploration of Europa.
Now, it's thought that the organic material that they're seeing there, did that come from Io, or did it come up from the underneath?
I think that the prevailing notion is that a lot of it came from Io. Of course, we can't tag it to its exact location, but we do observe Io very close to Europa, just spewing out organic material. And we observe organic material on the surface of Europa, and I think people want to put 2 and 2 together and say, yes, this is where it's coming from. But I'm not sure that there's any definitive evidence yet that that's actually the case. And to get back to Mateusz's question about what sort of complexity of life we would expect to find, I think the answer is probably very, very simple. Because although there's liquid water under the surface of Europa, there's not a lot of heat. And so there's not a lot of energy. And so you need animals or organisms that are very efficient at harvesting this energy. And that tends to be the very smallest organisms. And to go even one rung up the food ladder or the food chain and sort of have animals consuming those other ones, you have to have consume vastly more food as basically a carnivore in order to get the amount of energy that you need. And if you already have kind of an energy-starved environment, it might not be a likely place to find this sort of complex large life.
How do you think, how long did the life on Europa might have to evolve? Did it start just straight after formation of the moons of Saturn, of Jupiter?
So I think that we think that the ocean under the surface of Europa is very old. Whether it's as old as the solar system, that's challenging to answer, but it certainly appears like Europa has been in its present location for a very long time. And that would suggest that that ocean, powered by the tidal heat of Jupiter, has also been active for a very long time. So it's quite possible that life has had, many, many millions of years, if not billions of years, to evolve on Europa. But we can't know that for sure.
I want to ask you about a planet we haven't talked about yet, which is Venus. A study recently came out saying that Venus might have been quite habitable for quite a long time.
Yeah, Venus is a warning sign for our search for life, our search for habitable areas around other stars. Because if you take sort of the most basic definition of what it means to be habitable, then actually Venus, Earth, and Mars all fit that definition. And this is an observational definition. Obviously, we know that Mars and certainly Venus aren't habitable by our standards today. But if you apply the standards with which we search for habitable worlds around other stars, Venus shows up to be as or more habitable than planet Earth. And that tells us that earlier in the history of the solar system, when Venus had different conditions, it very likely was much more like Earth than it is today. And because it's so similar in size to the Earth, we could imagine conditions on early Venus being very similar to conditions on Earth today or even on early Earth.
There seems to be a lot of volcanic activity on Venus. Do you think that's what's caused the huge atmosphere and the problems with the environment there?
So volcanism certainly could have contributed to the thick atmosphere on Venus. For those of you who don't know, the atmosphere on Venus is around 90 times thicker than the atmosphere on Earth. It's equivalent basically to standing underneath a kilometer of ocean. So you're talking about walking along the bottom of the ocean, but temperatures many hundreds of degrees higher than on Earth at the same time. So this is a really scalding, crushing place to be. And I think sort of the favored theory for how Venus got the way it did today is this idea of the runaway greenhouse effect. So we experience the greenhouse effect here on the Earth. It's the idea that our atmosphere traps in heat, and that warms the planet up, and that can change the composition of the atmosphere, which can trap more heat, which can change the composition of the atmosphere more, trap more heat. And Venus closer to the sun than Earth, this would have happened more violently. And so what might have happened is early on in the history of the solar system, Venus had vast oceans just like the Earth. It also had a thick atmosphere. This greenhouse effect started causing more and more water to evaporate into the atmosphere of Venus. And water, turns out, it's actually a very good greenhouse gas. So that would raise the temperature of Venus and evaporate more of the oceans. And this cycle kind of continues until you boil away the oceans. And then you start baking all the gas, the water, the carbon dioxide, etc., out of the surface of Venus. And so you have this very dry, brittle surface on Venus. And the more stuff you add, the more heat you're able to trap. And it just keeps going and going until there's nothing left, basically, to put into the atmosphere. And today, the surface of Venus is actually hotter than the surface of Mercury, even though Venus is about twice as far away from the sun as is Mercury.
Yeah, it's quite ironic, actually, that that runaway greenhouse effect is probably one of the best candidates for a technique for terraforming Mars, but they start a lot lower. I believe they're like 70 degrees C lower average temperatures on Mars, so they've got quite a way to run before they get up to our temperatures. Yeah, so on Earth, we don't think the runaway greenhouse effect is possible through natural means. The Earth itself is far enough away from the sun that we're not in danger of becoming Venus. That doesn't mean we can't dramatically alter our environment and our atmosphere, but the idea of having an Earth in the future that has 50 or 100 times more atmosphere than we have today, that doesn't seem to be possible.
And so that's, I guess, positive in one respect, but we can do a ton of damage long before we reach that level. And that's what we're experiencing right now.
Morgan, do you think that our sun is actually expanding, and in about 1 billion or 1.5 billion years later we can actually end up like Venus?
So towards the end of the sun's lifetime, as it exits what we call the main sequence, and this is the period of a star's life where it's basically behaving like a normal regular star. What happens to stars is they tend to puff up. And the sun is of a kind of star that we would expect it to puff up enough that it actually, the surface of the sun could be pretty much at the orbit of the Earth. And so we could actually be a much worse version of Venus and actually be inside the sun. And that would obviously be a very bad day for anyone living here on the Earth. Or the sun could maybe expand a little bit less and we'd get much closer to the surface, in which case we absolutely could have the sort of effect that occurs on Venus. And it's kind of a toss-up. It's sort of a point of contention amongst astronomers, which one will happen first. Will the sun expand and swallow the Earth, or will the Milky Way galaxy collide with the nearby Andromeda galaxy? And obviously that's going to wreak havoc throughout the entire galaxy. Both of those should happen 4 to 5 billion years from now. And so if somehow our species manages to survive on our planet, we better have an escape plan to a nearby galaxy, because one way or the other, our galaxy's coming to get us.
Okay, anybody else?
Well, actually, I just was interested in a little bit of information. I know that, Morgan, you'll probably be an old man and still be working on Saturn and trying to find out the rings. And so I was wondering how you and your colleagues all managed to network and share information, and how large is this network, and what kinds of disciplines and other universities and academic entities are all engaged, touching antennae, so to speak, to get your answers before you are 120 years old?
Planetary science is an amazing field because it touches so many other fields. In a sense, planetary science is not its own field. It's an amalgam of all these other fields coming together to explain something as complicated as planets. So a lot of planetary science is geology that takes place especially on solid planets like Mars. A lot of it's chemistry, trying to explain how atmospheres trap heat or how life gets going. Some of it is physics. Just what I do is basically physics, talking about the interactions through gravity of individual particles in the rings. Once we start finding habitable planets out there in the galaxy, we'll start to bring in biology and the field of astrobiology. And so really the endeavor of planetary science is one of amalgamating all of these other fields together. And that means that there's an overwhelming, tremendous amount of material and expertise sort of in our grasp. And it can be, frankly, very daunting to try to integrate all of that and wield it in a useful way. One of the inventions of the last 15 years that have really changed things is the ability to rapidly and quickly share manuscripts and papers and things over the internet. We now have this thing called the archive, in which people can put up versions of their work as they sort of are works in progress and gather input from the community. Those are excellent places for us to exchange ideas that then go into things like meetings. But the bottom line is that we're bringing so many resources to bear on these questions of planetary science that often two people or two collections of people can be attacking the same problem from totally different areas and not even really realize that the other person or other group is working on this. And so we have a long way to go to try to build these bridges to make this happen, because it's certainly a waste of work for two groups to be working on the exact same thing just from different ways. We'd much rather have them work together, come up with a better, more complete answer even faster, so we can move on and try to answer other problems.
Oh, good. Now, I think we're going to wrap up soon. But if there's any more questions for Morgan from the panel, anybody want to have one more go? Okay. Well, what we'll do is go around each of you and let you sort of give us your final thoughts for this evening, and then or this morning, as the case may be, and then I'll let Morgan have the last word, and then I'll make a few announcements, and we'll say goodnight. So let's start with Adam.
Yeah, I'd like to thank Morgan for taking the time to speak to us. He's obviously someone that enjoys talking about science. I would have liked to ask him a bit more about his mission to foster scientific literacy in society and help people understand and appreciate science and technology. Is that something that you think is important, Morgan?
I think that it's absolutely critical. I think that today we live in a world in which our lives are shaped every day by science. You know, the fact that we're meeting here on several continents, having this podcast is shaped by science. You know, the fact that I went to the doctor the other day and got a vaccine, that's shaped by science. And it's very easy to get overwhelmed by sort of the sheer enormity of the scientific endeavor and lose track of the people that are behind that. And I think the fact that, you know, astronomy and especially planetary science are such exciting, engaging topics gives us a window into what it's like to do scientific investigation and to understand the incredible effort that scientists put in order to make these discoveries, and the mountain of evidence that stands behind claims that the scientific community makes. On the other hand, I think it's important for scientists to understand that what we do is informed by the public. You know, most of us, especially in astronomy and planetary science, we work for the public, either directly as a member of NASA or indirectly by a grant that ultimately is paid for by the taxpayers of the United States or the European Union or what have you. And it's important that we make an effort to connect what we're doing with everyone else, because science isn't just some camp out there in the wilderness, and we're not just hurling down discoveries from the pinnacle of Mount Science. You know, I was watching a football game this afternoon, and, you know, my friends were off running a marathon, and I want to connect the idea of doing science with everyday people and everyday activities. All of us can contribute to the scientific enterprise, and all of us should have endeavors and livelihoods outside of science as well.
Chris Prophet.
Okay. You've painted a lovely picture, fantastic illustration of how interesting and exciting it's going to be. Saturn, Jupiter, nuclear-powered torpedoes melting through ice to get to the life underneath inside. It can't come soon enough.
Okay, Marsha.
Well, I just wanted to kind of piggyback on my last question, that I often find that there is an awful lot of information out there that might even be collected, but is not being accessed. And I think there's a lot of cases in academia where there's just a reinvention of the wheel, that if there are ways now, certainly with computer systems. I was reading an article just recently about how to better share data. And I think that is really essential, because money's already been spent on gathering information and it gets dumped in this big bin. And now people have to dive in there and try to make sense of all that data. So that's one thing that I think is going to be exceedingly important in trying to figure out some of the mysteries you're looking at right now. I hope we can do it.
Okay, Mateusz.
Yeah, I just wanted to thank you guys, thank Morgan, and actually I wanted to thank Morgan for agreeing to participate in my blog, Astronomy Finest. So from now on, one of the contributors will be Morgan. Thank you.
Yeah, I understand it's really elite intellectuals in that, that group.
Oh dear.
Well, except for me. Well, okay. Morgan, any last thoughts?
Well, I'd certainly like to thank you guys for allowing me to come on the podcast this evening, and I hope that sometime I can come back and share with you a little bit more about my wonder at the universe. But I'd like to say to those listening, if you're not a scientist and you find this stuff really cool, then pitch in. If you like planetary science, map some craters using something like moon mappers from CosmoQuest. In just 5 minutes, you can contribute to what's turning out to be the most accurate catalog of craters in the solar system. If you like astronomy, check out something like Galaxy Zoo and help us identify new galaxies out there in the universe. And if you find something particularly unusual, it could even be named after you. There's so many ways today to get involved with just 5 minutes or 5 hours into making a real contribution to the wonderful world of astronomy and planetary science. And I think not only will you be helping people like me out, but I think you'll find it to be really exciting, really rewarding, and a whole heck of a lot of fun.
Oh, good recommendation. I also I do that from time to time. I like Planet Hunters especially. Well, that's it for this episode. This is episode 56 of the Unseen Podcast. We'd love to hear from our listeners. Please let us know what you think. You can always just email us at unseenpodcast@gmail.com, or you can come onto our blog at unseenpodcast.com and comment directly on the episode. Yeah, we will try to get Morgan back someday. And hopefully when there's some exciting new developments on the planetary science front, he'd be a good guy to give us some expert commentary on it. And I want to thank Adam for, I think it was you, Adam, right? That persuaded Morgan to come on. So
yeah, I've known Morgan. Well, it's a strange situation because he's never met me before, but I've seen Morgan virtually every week on the Weekly Space Hangout for the past few years.
Well, you also got Pamela Gay for us about a year ago. So
Josh, that's my secret source. Guess.
Okay, well, and see what else I wanted to say. Okay, yeah, by all means, check out all our websites and subreddits and so on, and
Facebook page.
And also, yeah, the next week, we've been normally on a 2-week rhythm, but next week we're recording another show, and Australian science fiction writer David Grigg will host. I'm not sure if I'll be in town or not. It's still kind of iffy. So, but by all means, you're going to want to tune to that, because that will be a different perspective than mine. And I love having guest hosts, and in fact, I encourage everyone who's been on the panel at least once or twice to give it a go. And it's I wouldn't mind if I was the host only once a month. That would be great. And by all means, if you'd like to be on the panel, you can be. This is an open participation podcast. Anyone can go to our Google Plus community, which is now a public community. Just join the community, and you will get invitations every 2 weeks to join a panel. There are some rights and responsibilities there. By all means, check out our frequently asked questions at unseenpodcast.com. It'll tell you everything that's involved in being a panelist, and what you need to do and what you don't need to do also. You don't need to buy expensive audio equipment. You just need to basically show up, and we will get you on the air. And I think that's it for us. I'd like to thank once again our special guest Morgan Rehnberg, Adam Smith, also known as Adam Synergy to you Google Plusers, and Chris Prophet, Marsha Barnhart, and Mateusz Macias. And that's episode 56. See you next time with host David Grigg. Bye.